We are continuing on the topic of state machines, FSMs, implementation of FSMs, starting with state diagrams. And as an example, we are doing sequence detectors. We did a Moore sequence detector, M-O-O-R-E, and then we are now doing a different kind of sequence detector, and we are doing a Mealy sequence detector. We compare the timing and so on. So let's go to that. So this is Mealy, and again, I'm doing the same thing. I'm detecting the sequence of 1, 0, 1, 1. Okay? And 1, 0, 1, 1. So again, I start in the state A and look for a 1 to go forward. Okay? Once I go forward, I get to state B. All right. As I'm going through this, I'm also listing my outputs. So when I'm in state A, I receive a 0, my output is 0. I receive a 1, my output is 0. Okay, that's different from the Mealy, the Moore machine, that in a particular state, your output is also specified. Doesn't depend on the inputs. Here, I'm talking about them depending on the input, the outputs depending on the inputs as well. Something I mentioned it was when you're talking about a particular state, like a state B, for example, the circle and all the edges that get out of it is part of the state. And therefore, we are saying while I'm in B, a 1 takes me back to state B with a 0 output. While I'm in state B, a 0 takes me to state C with a 0 output. Okay, so following the 1, 0, 1, 1, 1, 0 takes me to state C. A 1 takes me to state D. This is where I am now. A 1, 0, 1 takes me to state D. But then in state D, if I receive another 1, the output becomes 1. So I don't wait until I go to the next state to make the output 1. I say while I'm in state D, a 1 on the input makes the output 1. And therefore, I have detected 1, 0, 1, 1, starting from state A back to state B. Why do I go back to state B? Because I'm looking for 1, 0, 1, 1. Right? I'm looking for 1, 0, 1, 1. And if I receive another 1, 0, 1, 1, if I receive a 1, that could be the beginning of another 1, 0, 1, 1. And therefore, I go to state B, where a 1 is saved. So let's do the, remember, let's do the, this is the state diagram. Oops. Okay. State diagram. That's the front end of our processing. Then we do state table. Then we do transition table. Then we do excitation table. Then we do K-maps. Then we do circuit diagram. And then we are done. Okay? So let's go through all these steps, starting with what you see in front of you. State table, all it is turn the circular thing, or the state diagram, into a tabular form. So this is my state table. Okay? Again, let's look at the B example. Okay, while I'm in state B, while I'm in state B, a 0 on the J input. That is not marked, but that's J. Let me correct this. This is J, this is J. Okay. While I'm in state B, a 0, a 0 on J, a 0 on J, takes me to state C. Okay. While I'm in state B, a 1 on J, a 1 on J, takes me back to state B, and I should have marked the state C. Okay. And then, while I'm in state B, a 0 on J gives me a 0 output. While I am in this state, a 1 on J gives me a 0 output. Okay? So that's how everything is set up. And then once I have this, then the next step is, as we said before, transition. From transition table, you have to from state table. This was the state table. You have to decide the state assignment, and I give A00. Remember, I say it doesn't make any difference how you assign the state as long as they are unique states. So I give 0, 0 to A, 0, 1 to B, I give 1, 1 to C, and I give 1, 0 to D. Okay, this is my state assignment, which is what is over here for A, B, C, D. And then what I do the same as what I did before. In this state table, wherever I have A, I put 0, 1, 0, 0. Whenever I have B, I put 0, 1, and so on. That gives me my transition table. Transition table has some timing involved. That means after the clock. I have to decide what kind of flip-flop I want, which is in this case, again, I'm going to be using D. And based on that, I'm going to come up with the excitation table. Okay, so what I did is I decided on the D flip-flop type. And now I have the excitation table. The beauty of this is that the excitation table here has only 4 states, 2 state variables, 1 fewer than the previous state number of state variables. This is a Mealy machine. Mealy machines usually have 1 fewer state. Okay, notice that the other one also had an E state. I don't have an E state here. So here is the excitation table and the output table. But you pay for it by the output depends on the input as well as the output, as well as the states. So notice that for the Moore machine, the J input did not participate in the output, whereas here the J input does participate in the output. Remember that. In the Moore machine, I had 3 state variables. For each of them, I had 4 variables, the input and the 3 state variables. Okay, in here, I have only 2 state variables, the J input and the 2 state variables, and therefore I have 2 3 variable maps. Then, since J is also participating in the determination of output, therefore I also have a 3 state variable kernel map for the W output. And the reason I did 000111110 for the state assignment, because this maps nicely to the kernel map. So what I'm really doing is I'm taking this as one kernel map, which is D1. I'm taking this as my second Carnot map, which is this for D0. And then my third Carnot map is this for W, which is this. Okay, so the left column is the J0, the right column is J1. Okay, like this. And then what I have is doing the implementation. Look, here I have D1 is this. D1 is this, this. And if it were this, it would be XOR of V1, V0, J. Okay? But since I don't have that, so if I had a 1 here, it would be the XOR of all this. So I go ahead and do the XOR all the 3 inputs anyway, and then AND it with the complement of this map here. This map is J V1 bar. Complement of it is this. ANDing with this means that the extra one that I get with the XOR is zeroed out, and therefore I come up with D1. Okay? So that's for the D1. Let's look at this one here. This one, the D0, I have this, and I have this, which is XOR of V1, V0. Okay? So that satisfies that, except that now I have a extra 1 over here. So what I do is, remember I took the 1, 1, complemented it. Now I'm going to take that one, don't complement it, and OR that with the XOR of V1, V0. Okay? And therefore, that becomes the 1, 1 here, ORing it with the XOR that puts a 1 on the upper right-hand corner. And complementing it and ANDing it removes the 1 on the upper right-hand corner for the green map. And so that's it. And then for the output, I have J V1 V0 bar, which is this for the red one. All right, let's do the circuit. This is the XOR and then XOR again with J. But then V1, V0 XOR, then I OR it with the V1 J, that gives me D0. Then I take V1 bar J and complement it, and it with the 3 XOR thing, this thing here, and therefore I get the input D1. So that gives me D0, D1. Remember, D0, D1 is taken from the excitation maps. But then what I really want, I want the transition maps. Okay? And therefore, I put the D1, D0 inside 2 flip-flops, the D inputs of 2 flip-flops. And that gives me V1 plus, V0 plus. That means at a time later. Those go feedback and then come back into V1, V0. That gives me my complete circuit. Notice once again that I have a combinational block and a sequential block. The sequential block sits on the feedback path of the combinational output and input. This is my present state, and the inputs going from the combinational to the flip-flops, that's my next state. And this is the primary output, this is the primary input, P in, P out. You want to write Verilog, as simple as what you did before, and there is one little difference which will be showing. All right, so once again, I have the model as a combinational block, a a combinational block and a register block, which is the this is the present state, this is the next state. Okay, and then for the combinational block, I have the primary input, which in this case is nothing but just W. Okay, this is W. This is my out. No, sorry. This is J. This is my output W. Those are present state and next state. And also down here, I have the clock and the reset, which I don't really interfere with. Okay. So let's show the Verilog, the Verilog code as it corresponds to this block diagram I'm showing. See the J input, the present state form the next state output, and therefore it's this always block here. Okay. And then the J input, I will come back to all of this. The J input, the present state form the W block, which is this one over here. And then the register part is this always the statement over here. Okay? Once again, this is asynchronous positive edge clock. Asynchronous reset, positive edge clock. All right, I'm declaring my present state and next state, and this is the present state that is fed back. This is the next state, which is the input of the flip-flops. I'm declaring them right over here. Okay? Remember how we said 000 is A, 001 is B, and this and all that. And then we had to remember, okay, 000 is A, and so on. Instead of doing this, what I'm showing here is I'm showing a parameter, a 2-bit parameter. A equal 2 tick B00. B equal 2 tick B01. C equal 2 tick B11. And D equal 2 tick B10. That means I'm giving these parameters a value. From this point on, I don't really have to worry about the numbers anymore. For the case choices, I use A, B, C, D, much cuter, much nicer description, and much more readable. Let's look inside the transition always statement. The transition always statement starts on line 5. It has the present state and J as its input on its sensitivity list. Well, look at the dark red bubble I'm showing on the right hand side. It has present state and J as its inputs, and therefore these are the same thing. Then I have on line 6, I have next state equal to A. Okay, what is this? A is a parameter. That's the 00 parameter. So instead of saying next state or the output in its inactive value is 00, instead of doing that, I just say next state equal to A, and then A is that parameter that I just defined, and I'm using that. All right, then on line 7, I start the case statement. Case looking at the present state. Present state is the input of that dark red circle. Then on line 8, okay, on line 8, I'm looking at the state A. I'm looking at the state A on line 8. In the state A, if J is 1, my next state is B. Just read this. See, this and this correspond exactly. If J is 1, my next state is B. I'm not saying anything about the output, remember. Okay, we are not doing this in there. We are doing that in the dark blue circle that defines W. And then on line 9, I have state B. State B is, let's see what other color I can use here. Yeah, perhaps black. State B is if the present state is B, J is 1, then the next state is B. Otherwise, the next state is C. And this corresponds to this line over here. Okay? And then the same thing for the rest of them. Also, I always put a default. Next state, I don't anticipate default to be ever activated. But if it does ever, next state becomes A. That means that initial A state. So that takes care of my block for setting the next state. Let's look at the dark blue block for setting the output on the right hand side. This one over here. That corresponds to this assign over here. Okay, I could do always if I wanted, but it's so easy, it's so simple that I can just do an assign statement. Remember, let's look at the output. When I'm in state D, if the input is 0, the output is 0. If the input is 1, the output is 1. And therefore, read line 16. It says the output is when my present state is D, then J, otherwise 0. Okay? What it means is if I'm in state D, my output follows the input. And finally, the last one here, that's the register block. This one over here, it is asynchronous reset. It is positive edge. If the reset is 1, A goes into the present state. The present state is the output of the flip-flop. Otherwise, next state goes into the present state. This is the timing diagram. Okay, let's look at the timing diagram. Let me draw the state machine here again. It is 1011 detector, 1, 0, 1. Okay, this is state A, B, C, D. 0 goes back to this, 0. When I'm in state B, 0 takes me forward, a 1 leaves me here with 0 output. 1, 1, 0. I'm in C. If C, I receive a 1, I still have a 0 output. In C, if I receive a 0, that's bad. That's almost the end of the world. A 0 gives me a 0. Now I'm in the state D. 1, 0, 1. I'm in D. If I receive a 0, then there is a possibility of 1, 0, and then another 1, and therefore I go to C, 0, with a 0 output. But then if I'm in 1, 0, 1, 1 in D, I get a 1 output, and therefore I'm going to erase all of this. I'm going to get a 1 output, and then go to state B. 1, 1 output. Okay, let me quickly check with what I have here, and yeah, it does look good. Okay, fine. Let's trace the states. Initially, let's say I'm in state A. If I'm in state A initially, here, a 1 on the input, just follow what I'm showing there, takes me to state B. When I'm in state B, a 0 on the input takes me to state C. When I'm in C, a 1 on the input, okay, a 1 on the input takes me to state D. When I'm in state D, a 1 on the input takes me to state B. Don't worry about the outputs yet. When I'm in state B, okay, when I'm in state B, a 0 on the input takes me to state C. When I'm in state C, a 1 on the input takes me to state D. When I'm in state D, a 1 on the input. This is a 1 on the input. Takes me to state B. When I'm in state B, a 1 on the input, a 1 on the input takes me to state B. And when I am in state B, a 0 on the input takes me to state C. When I'm in state C, a 1 on the input takes me to state D. Okay? These are the Mealy machine states. And if you look at the Moore machine states, they were different than this. And I'm showing the output of the Moore and output of the Mealy. Now let's look at the output of the Mealy. The output of the Mealy is 1 whenever you are in state D. Okay, look, if you are in state D, and if you are in state D, whatever happens to your input happens to your output. Okay, that's why you say that everywhere else I have everything 0. But then when you are in state D, because your input is 1, as soon as you come into state D, which is, I'm looking at this one over here. As soon as you come into state D, because that happens after, a little bit after the clock, therefore your output is 1. Your output stays 1 for as long as you are in state D. When do you get out of state D? When the clock arrives a little bit after that, and therefore clear through the next edge of the clock, you stay in state D, and therefore your output in Mealy for this part follows this input, and this is it. Then you come into this other D state. As soon as you come into the D state, your input is 1. That 1 transfers over to the output, and therefore your output becomes a 1. But then a little shorter after that, the input becomes 0. The input becomes 0. The output gets a glitch and then comes back to 0. And then later on, it comes back on. Your output becomes 1. But then your output stays 1 because the input hasn't changed, clear through the next edge of the clock. And then that's it. Now, how many 1s do you see on the output? I only see 2 because I have only seen 1 0, 1 1, 0 1, 1 1, 0 1. Okay, that's 1 1 0 1 1 sequence. This is 1 1 0 1 1 sequence, and that's it. And therefore, I better see only 2 1s on the output. But then you say, no, there's another one. I don't see that one. I don't even consider that. I don't even look at it. Because that's not coinciding with the active edge of the clock. The only 2 1s on the Mealy output that coincide with the edge of the clock, that's the active edge of the clock, which is the rising in this particular case, are in these 2 places. Okay? I give you that this is different than Moore. It is happening sooner, but the number is the same. You have 2 places where your Moore machine issues a 1. You have 2 places where your Mealy machine also issues a 1. Mealy happens sooner. Actually, that's the advantage of Mealy. The good thing about Mealy is Mealy machines react faster. Okay, that's why it's important to use Mealy sometimes. Moore machines are precisely timed according to clock. Look at this. Look at the Moore machine output here, which is the same thing what I showed at the end of the previous part. Okay? No matter what happens, the duration of a Moore output is exactly the same as a clock period. Okay? So it has a better timing. Moore machine uses one more state than the Mealy machine. Okay? So there's no free lunch. You get a more precise timing, a little bit more hardware. If input changes in the Moore machine between the clocks, the output doesn't change a bit. Look at the Mealy machine. The input changes. Even if the input changed here, my output would change as well. Okay, but with the Moore machine, that doesn't happen. Even in the Mealy machine, even the output changes, but since it's not coinciding with the clock, I don't care. Synchronous with the clock, asynchronous with the clock. And now let's go back to the Verilog description and see the Verilog description here. Look at the dark blue and the dark blue here. The output, read this, read line 16. It says, line 16 says the output is, if the present state equal to D, the output is J. That means the output depends on J. Okay? But in the Moore machine, if you go back and look at the Verilog description there, you see that the output only depends on the state. And I'm going to show you the circuit diagram. Then again, you are seeing that J here participates in the termination of the output. Okay? You want to see that in, this is the Mealy machine. You want to see that in Moore machine, here it is. The dark blue, line 17. The output only depends on the present state and nothing else. You want to see the circuit? The output only depends on the state variables and not the J input. Okay? You want to see the timing? Okay? See, the same timing I have over there, which the output is only 1 during the time that you are in state E. All right, where are we now? We have done the circuit for the Mealy, the timing diagram for the Mealy, comparison between Mealy and Moore, and what we're going to be doing next is talk about Huffman model. There is really not much to saying about Huffman model. We have already seen it. All I'm saying is formulating now. Okay, formulating means this. Every sequential circuit under the blue sky has a combinational part with feedback through a register part. Register controls only go to the register part. Synchronous reset, asynchronous reset, synchronous set, asynchronous reset, enable, whatever you have goes in the register part. Doesn't even get involved in the functionality of your circuit. Then you have the combinational part. The combinational part takes the primary inputs, produces the primary outputs. There are two combinationals. One is producing the primary outputs, and another one producing the next state. Okay, these three blocks are concurrent blocks in a Verilog module description. You can do all three of them using always the statements, or you can, if it's a simple one, you can do that with a sign statement, which we did for the primary outputs. This is called Huffman model. This goes back to a 1954 paper that builds a sequential circuit out of passive elements. Okay, R, L, and C. So the theory goes back that far. And not only state machines, but also the complete RT level design follows the same rule. When you are doing state machines, it's always very good to follow the Huffman model. And also when you're doing the Verilog description, follow this. Okay, and what I've shown you so far is exactly this, that you use the Verilog description according to this Huffman model, and then for each of these blocks you have 1 or 2 lines of code, and then you know exactly what you're doing. You know that when you're describing the green part, the register part, the input signal doesn't participate there. When you are doing the next state part, the dark red part, the reset or the preset of the flip-flop don't participate there. All right, let's talk about some more implementations later. Okay.